Tonight, we're going to confront one of the strangest facts in all of physics. There is a field, invisible and silent, filling every cubic centimetre of the universe right now, and without it, every fundamental particle in existence would be massless. Electrons would have no mass. The particles that carry the weak nuclear force would have no mass. The atoms that make up your body could not exist. Nothing with structure, nothing with weight, nothing solid or lasting would be possible. This field is always on. It never drops to zero. It has been switched on since a fraction of a second after the Big Bang, and it is on right now, passing through you, through the walls, through the empty space between galaxies. And when you disturb this field in just the right way, a particle briefly appears. That particle is the Higgs boson. But what is it actually made of? And why does everything depend on it? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with a question that sounds straightforward, but is actually one of the most misunderstood questions in modern physics. What is the Higgs boson made of? You hear people ask this all the time. It seems like a reasonable thing to wonder. When you learn about atoms, you find out they're made of protons, neutrons, and electrons. When you learn about protons and neutrons, you find out they're made of quarks held together by gluons. So naturally, when someone hears about the Higgs boson, they want to know what's inside it. What are its parts? What smaller pieces combine to create it? But this question contains a hidden assumption. It assumes the Higgs boson must be built from something smaller. It assumes it must be a composite object, a structure assembled from constituents the way a proton is assembled from quarks. And as far as our best physics tells us right now, that assumption is wrong. The Higgs boson, in the standard model of particle physics, is not treated as a composite object. It does not contain smaller, known parts. It is classified as a fundamental particle. It sits at the same level as an electron or a quark, not built from pieces, but existing as a basic, irreducible entity of nature. Now, that might sound like a dead end. If the Higgs boson isn't made of anything, then what is there to talk about? But the answer is actually far more interesting than internal structure would be, because the Higgs boson is something specific. It is an excitation of a quantum field, and understanding what that means, understanding the difference between the particle and the field it comes from, is the key to understanding why the Higgs matters at all. It is the key to understanding why mass exists. To get there, we need to talk about what modern physics actually says particles are, because the picture most people carry in their heads is wrong. Most people imagine particles as tiny solid objects, little spheres flying through space, bouncing off each other like billiard balls. This image comes from centuries of intuition. We live in a world of solid objects, rocks, tables, baseballs. When scientists said atoms were particles, people imagined tiny rocks. When they said electrons were particles, people imagined even tinier rocks orbiting a nucleus like planets around a star. But quantum field theory, the framework that underlies all of modern particle physics, tells a completely different story. In quantum field theory, the fundamental ingredient of reality is not a particle, it is a field. A quantum field is something that exists at every point in space and time. It fills the entire universe. It has a value everywhere, at every location, at every moment. Think of it loosely like a medium that extends through all of space. Not a physical substance you could touch or bottle up, but a mathematical and physical entity that permeates everything. And here is the crucial point. A particle is what you get when a quantum field is disturbed. When energy is added to a field in a localized way, the field vibrates. That vibration, that localized ripple of energy in the field, is what we detect as a particle. An electron is not a tiny ball sitting somewhere in space. An electron is a ripple in the electron field. A photon is not a little pellet of light. A photon is a ripple in the electromagnetic field. A quark is a ripple in a quark field. Every fundamental particle in the standard model corresponds to a specific quantum field, and every particle is simply an excitation, a disturbance, a vibration of its corresponding field. This is not a metaphor. This is not a loose analogy designed to make things easier to picture. This is the actual mathematical description that physicists use. The equations of quantum field theory describe fields, not particles. Particles emerge from those equations as quantized excitations. The word quantized is important here. It means the excitations come in discrete lumps. You can have one electron or two electrons, but you cannot have one and a third electrons. The field vibrates in whole units. Each unit is a particle. Let me try to make this more concrete. Imagine a perfectly calm lake. The surface is flat, undisturbed. This is the field in its ground state, its lowest energy configuration. Now drop a stone into the lake. Ripples spread outward from the point of impact. Those ripples are disturbances in the surface. They carry energy, they propagate, they can interact with other ripples. In this loose analogy, the lake's surface is the field and the ripples are the particles. But there's an important difference between a lake and a quantum field. On a lake, ripples can have any size and any energy. You can make a tiny ripple or a huge wave or anything in between. Quantum fields don't work that way. Their excitations come in specific, discrete packets. You either have a full particle or you don't. There's no such thing as half a photon in free space. The field either has an excitation at a given energy or it doesn't. This discreteness, this quantization, is what puts the quantum in quantum field theory. Now, every fundamental particle in the Standard Model has a corresponding field. There is an electron field filling all of space. There is a muon field filling all of space. There are quark fields, one for each type of quark. There is the electromagnetic field whose excitations are photons. There are fields for the W and Z bosons, the carriers of the weak nuclear force. There are gluon fields for the strong nuclear force. And there is the Higgs field. The Higgs boson is the excitation of the Higgs field. It is the ripple you get when you add energy to the Higgs field in a concentrated, localized way. This means the Higgs boson is not made of smaller parts, any more than an electron is made of smaller parts. In the Standard Model, both are fundamental excitations of fundamental fields. Both are elementary. Both sit at the bottom level of the known structure of matter. You cannot open up an electron and find gears inside. Similarly, you cannot open up a Higgs boson and find constituents. As far as the mathematics and experiments tell us, the Higgs boson is a point-like fundamental particle. It has properties. It has a mass. It has zero electric charge. It has zero spin, which actually makes it unique among all known fundamental particles. It's the only fundamental particle we've discovered with spin zero. But it does not have internal structure in the way a proton has internal structure. This is a genuinely important distinction. A proton is not a fundamental particle. A proton is a composite object. It's made of two up quarks and one down quark bound together by gluons, the carriers of the strong nuclear force. The quarks inside a proton are constantly interacting, exchanging gluons, creating and annihilating quark-antiquark pairs. The interior of a proton is a roiling, dynamic, unimaginably complex environment. You can probe a proton's internal structure. You can scatter electrons off it at high energies and see that the electrons bounce off individual quarks inside. This is exactly what experiments at the Stanford Linear Accelerator Center did in the late 1960s and early 1970s, earning Jerome Friedman, Henry Kendall, and Richard Taylor the Nobel Prize. But when you do the same kind of experiments with the Higgs boson, when you study how it's produced and how it decays at the Large Hadron Collider, there is no evidence of internal structure. The Higgs boson behaves exactly as the Standard Model predicts. A fundamental, structureless, point-like particle should behave. It interacts with other particles in precise, predictable ways that match the mathematics of a fundamental scalar field. There are no surprises, no anomalies, no hints of compositeness. Now, could the Higgs boson turn out to be composite? Could future experiments at higher energies reveal that the Higgs is actually built from something smaller? In principle, yes. There are theoretical models, collectively sometimes called composite Higgs models, that propose exactly this. In these models, the Higgs boson is not a fundamental particle, but a bound state of new, as yet undiscovered particles, held together by a new, as yet undiscovered force. These models are taken seriously by some physicists. They're studied, they're calculated, they make predictions. But so far, no experiment has found any evidence supporting them. Every measurement of the Higgs boson's properties at the Large Hadron Collider is consistent with it being fundamental. The simplest explanation that fits all current data is that the Higgs boson is exactly what the standard model says it is. An elementary excitation of the Higgs field, not composite, not built from parts, fundamental. So when someone asks what the Higgs boson is made of, the honest answer from current physics is that it isn't made of anything in the way people usually mean. It's a quantum of the Higgs field. It's a ripple in a field that extends through all of space. And asking what it's made of is a bit like asking what an ocean wave is made of. The wave isn't made of something separate from the ocean. The wave is the ocean, disturbed. The Higgs boson isn't made of something separate from the Higgs field. The Higgs boson is the Higgs field, excited. But this only deepens the mystery. Because if the Higgs boson is just a ripple in a field, why does everyone treat it as so special? What makes the Higgs field different from all the other fields? The electron field has excitations too. Those excitations are electrons. The electromagnetic field has excitations. Those are photons. Every field has its particle. So what's the big deal about this particular field and this particular particle? The answer is that the Higgs field does something no other known field does. It has a non-zero value in its ground state. And this single fact is responsible for one of the most important features of the universe: mass. But to understand that, we first need to understand what ground state means and why a non-zero ground state is so extraordinary. Every quantum field has a ground state. The ground state is the lowest energy configuration of the field. It's what the field looks like when it's completely calm, when there are no particles present, when nothing is happening. For most fields, the ground state is simple. The field value is zero everywhere. Take the electromagnetic field. In its ground state, with no photons anywhere, the electromagnetic field has a value of zero at every point in space. It's completely empty, completely calm. If you add energy, you create photons, ripples in the field. But when you remove all the photons, the field settles back to zero. The same is true for the electron field, the quark fields, and the gluon fields in the simplest description. In their ground states, with no particles present, these fields have a value of zero. The vacuum, empty space with nothing in it, is a state where all these fields sit at zero. They're ready to be excited, ready to produce particles if energy is supplied, but in their resting configuration, they're at zero. The Higgs field is different. Its ground state, its lowest energy configuration, is not at zero. The Higgs field's value in empty space is about 246 billion electron volts. That number is measured, not chosen. It comes from experiments. It's set by the properties of the weak nuclear force, and it is not zero. The Higgs field, even in the most perfect vacuum you could ever create, even in the emptiest stretch of intergalactic space, has a non-zero value. It's always on, it's always there. It never turns off. This is what makes the Higgs field unique among all the fields we know about. It's the only field in the standard model whose vacuum expectation value, the value it takes in its lowest energy state, is not zero. Every other field sits at zero when undisturbed. The Higgs field sits at 246 billion electron volts when undisturbed. That is its natural resting state. To push it to zero would actually require adding energy. Zero is not the lowest energy state for the Higgs field. It's a higher energy state. This might sound abstract, but it has a concrete and dramatic consequence. Because other particles interact with the Higgs field, and because the Higgs field is always on, always filling space with its non-zero value, those particles are always interacting with it. They're never in a region where the Higgs field is zero. They're always swimming through it, always coupling to it. And this permanent, unavoidable interaction is what gives those particles mass. We'll get into the details of exactly how this works, but for now, the key insight is this. The Higgs boson and the Higgs field are not the same thing. The boson is the particle. It's the ripple. It's the brief, localized excitation that appears when you add a lot of energy to the field. It was detected at the Large Hadron Collider in 2012, and it exists for an unimaginably short time, roughly 1.6 times 10 to the negative 22 seconds, before it decays into other particles. The Higgs boson is fleeting, it's rare, it's hard to create, it requires enormous energy to produce. The Higgs field, on the other hand, is everywhere. It's permanent. It doesn't decay. It doesn't need to be created. It has been filling all of space since a fraction of a second after the Big Bang. It's in this room right now. It's inside your body. It's between you and the nearest star. It never switches off. The Higgs field is arguably the most important entity in the Standard Model because it is responsible for the masses of fundamental particles. The Higgs boson is merely a consequence of the field. It's what happens when you poke the field hard enough. Most of the popular excitement around the Higgs focused on the boson. That makes sense. The boson is what you can detect. It's what shows up in particle detectors as a bump in a graph, a statistical excess of events at a specific energy. It's what earned Peter Higgs and Francois Englert the Nobel Prize in 2013. But from a physics perspective, the boson is almost a side note compared to the field. The field is what matters. The field is what gives mass. The boson is just evidence that the field exists and has the properties we think it does. Detecting the Higgs boson was critically important because it confirmed the existence and nature of the Higgs field. But it is the field, not the boson, that shapes the universe. Think of it this way. Imagine you're studying the ocean. The ocean covers most of Earth's surface. It affects climate, supports ecosystems, shapes continents. The ocean is enormously important. Now imagine someone creates a particularly large wave. That wave is dramatic, it's measurable, it might even be newsworthy. But the wave is not the ocean. The wave is a disturbance in the ocean. The ocean was there before the wave and will be there after the wave subsides. The ocean's importance comes from the fact that it's always there, always covering the surface, always interacting with everything around it. The wave is interesting and informative, but it's the ocean that matters. The Higgs boson is the wave. The Higgs field is the ocean. Now, you might be wondering how physicists arrived at this picture. How did they figure out that there must be a field filling all of space, always at a non-zero value, responsible for giving particles their masses? The answer traces back to a deep problem in the mathematics of the Standard Model, a problem that, without the Higgs field, would make the theory either inconsistent or completely wrong. In the early 1960s, physicists were constructing what would eventually become the Standard Model. They were building mathematical descriptions of the fundamental forces using a framework called gauge theory. Gauge theories are incredibly powerful. They describe forces through symmetries. The electromagnetic force arises from a symmetry. The strong nuclear force arises from a symmetry. The weak nuclear force arises from a symmetry. Each symmetry corresponds to a set of force-carrying particles. The photon carries the electromagnetic force. The gluons carry the strong force. The W and Z bosons carry the weak force. But gauge theories had a strict requirement. The mathematical symmetries that make these theories work demand that the force-carrying particles be massless. This is built into the mathematics at a deep level. If you write down a gauge theory and try to simply insert a mass for the force-carrying particles by hand, the theory breaks. The calculations produce nonsensical results. Probabilities that should be between 0 and 1 become infinite. The theory loses its predictive power. It becomes mathematically inconsistent. For the photon, This was fine. The photon is massless. Electromagnetism has infinite range. Everything was consistent. For the gluons, this was also fine in a different way, because the strong force has its own mechanism called confinement that keeps gluons from propagating freely over long distances, even though they are technically massless. But for the weak force, there was a serious problem. The W and Z bosons are not massless. They are extremely heavy. The W boson has a mass of about 80.4 billion electron volts. The Z boson has a mass of about 91.2 billion electron volts. These are among the heaviest known fundamental particles, about 85 to 97 times heavier than a proton. This mass is the reason the weak force has such a short range. Massive force carriers can only travel a short distance before they decay, so the force they carry only operates over extremely small distances, roughly 1,000th the diameter of a proton. The experimental evidence was unambiguous. The W and Z bosons were massive. But the gauge theory mathematics said they had to be massless. Something had to give. This was the crisis that the Higgs mechanism resolved. In 1964, several groups of physicists independently proposed a solution. Peter Higgs in Edinburgh published a paper. François Englert and Robert Brout in Brussels published a paper. Gerald Guralnick, Carl Hagen, and Tom Kibble in London published a paper. The core idea, developed slightly differently in each case, was that you could start with a gauge theory where the force carriers were massless, as the mathematics required, and then introduce a new field, a scalar field, with a very special property. This field would have a non-zero value in its lowest energy state. When this field settled into its non-zero ground state, it would interact with the force carriers, and through this interaction, the force carriers would behave as though they had acquired mass. The symmetry of the underlying theory wasn't destroyed, it was hidden, broken spontaneously. The mathematics remained consistent, the probabilities remained sensible, but the particles in the theory gained mass through their interaction with the ever-present non-zero background value of this new field. This was the Higgs mechanism, and the field responsible for it was the Higgs field. The theory predicted that the field would have its own excitation, its own particle, a massive scalar boson with spin 0. That particle was the Higgs boson, and for nearly 5 decades, physicists searched for it, building larger and more powerful particle accelerators, pushing to higher and higher energies, looking for the telltale signature of a Higgs boson being created and decaying. The search lasted from 1964 until 2012, almost half a century. It required the construction of the Large Hadron Collider, the most complex and expensive scientific instrument ever built, a circular tunnel 27 kilometers in circumference beneath the border of France and Switzerland. Superconducting magnets cooled to temperatures colder than outer space. 2 beams of protons accelerated to 99.9999991% of the speed of light, traveling in opposite directions around the ring, and smashed together at 4 points where enormous detectors stood waiting to capture the debris. On the 4th of July, 2012, 2 independent experiments at the Large Hadron Collider, called ATLAS and CMS, simultaneously announced they had found a new particle consistent with the Higgs boson. Its mass was about 125 billion electron volts. Its spin was 0. Its other properties matched the predictions of the Standard Model. The Higgs boson had been found. The Higgs field was real. But finding the boson was never really the point. The point was confirming the field. The point was confirming that there exists a quantum field filling all of space with a non-zero value, interacting with other particles, giving them mass. The boson was the proof. The field was the prize. And now we can return to our original question with a much clearer answer. What is the Higgs boson made of? It is not made of smaller parts. It is a fundamental excitation of the Higgs field, the only field in the Standard Model with a non-zero vacuum expectation value. It is a ripple in the field that gives mass to fundamental particles. It is the quantum signature of the mechanism that makes matter as we know it possible. And to understand why mass depends on it, we need to look more closely at this field that never turns off. To understand why the Higgs field is so extraordinary, You first need to appreciate just how strange it is for a field to have a non-zero value in empty space. This is not a normal thing. In fact, among all the fields in the standard model of particle physics, the Higgs field is the only one that does this. Every other fundamental field sits at zero when the universe is in its lowest energy state. The Higgs field does not. It sits at a specific, measured, non-zero value. And this single peculiarity is responsible for one of the most fundamental features of the physical world. Without it, the universe would be unrecognizable. Let me explain what it means for a field to have a value in empty space. We talked about quantum fields being entities that exist at every point in space and time. Each field has a value at every location. When there are no particles around, when the field is in its ground state, that value is typically zero. Consider the electromagnetic field. In a region of space with no photons, no light, no radiation of any kind, the electromagnetic field has a value of zero. It's there, it exists as a field. It's ready to support excitations if energy is supplied, but its resting value is zero. The same goes for the electron field. In a region of space with no electrons and no positrons, the electron field is in its ground state, and that ground state corresponds to a field value of zero. This makes intuitive sense. Empty space should be empty. If there are no particles, the fields should be at their lowest, calmest, most uneventful configuration. And for most fields, that calm configuration is zero. Nothing is happening. No excitations. No energy stored in the field beyond the unavoidable quantum fluctuations that exist in any quantum system. But the Higgs field breaks this pattern completely. The lowest energy state of the Higgs field, the configuration it naturally settles into when left alone, is not zero. It is a specific non-zero value, everywhere, at every point in the universe, in the emptiest vacuum you could ever imagine, in the vast stretches of intergalactic space where there is essentially nothing. The Higgs field is sitting at roughly 246 billion electron volts. That is its resting state. That is what empty space looks like from the perspective of the Higgs field. Not zero, not calm, always on. To appreciate how peculiar this is, think about potential energy and what it means for a system to find its lowest energy state. In everyday life, objects tend to settle into configurations that minimize their energy. A ball released on a hillside rolls downward. It doesn't stop on the slope. It rolls to the bottom of the valley and stays there. The bottom of the valley is the lowest energy state. The ball is stable there because any movement in any direction would take it uphill, requiring energy. Now imagine a very unusual valley. Instead of having its lowest point at the center, imagine a valley shaped like the bottom of a wine bottle. There's a hump in the middle, and the lowest points form a circular trough around that hump. If you placed a ball at the very center, at the top of the hump, it would be in an unstable position. Any tiny nudge would cause it to roll off the hump and settle into the circular trough at the bottom. The ball wouldn't end up at the center, it would end up somewhere in the ring around the center. The lowest energy state is not at the center, it's off to the side. This is, very roughly, the shape of the Higgs field's potential energy. The field's energy is not minimized when the field value is zero. Zero is like the top of the hump. It's a local maximum of the potential, not a minimum. The field's energy is minimized when the field takes on a non-zero value. The lowest energy configuration is out in the trough, away from zero. When the Higgs field settles into its ground state, it doesn't settle at zero. It settles at a non-zero value, somewhere in the trough of this wine bottle-shaped potential. Physicists call the shape of this potential the Mexican hat potential, because when you plot it in the right number of dimensions, it looks like a wide-brimmed hat with a bump in the center. The brim of the hat is the low-energy trough. The bump is the unstable point at zero field value, and the Higgs field, like a ball rolling off the bump, naturally settles into the brim. The specific value the field settles into is called the vacuum expectation value. For the Higgs field, this value is approximately 246 billion electron volts. This number is not predicted from first principles, it is determined by measurements of the weak nuclear force. Specifically, it's related to the masses of the W and Z bosons and the strength of the weak interaction. The vacuum expectation value is a measured constant of nature and it sets the scale for electroweak physics. Now, here is where things get really interesting. The fact that the Higgs field settles into a non-zero value means the universe is filled with this background field. Everywhere. Always. It doesn't oscillate. It doesn't propagate. It just sits there at its non-zero value, uniform and constant, filling all of space like a perfectly still ocean. Particles moving through the universe are always moving through this background. They can never escape it. There is nowhere in the universe where the Higgs field is zero in its ground state. This background field is not something you can detect directly in everyday life. You don't feel it. You can't see it. It doesn't push you or slow you down in any obvious way. But it does something profoundly important. It changes the fundamental behavior of certain particles. Particles that interact with the Higgs field, that couple to it, behave differently because of this ever-present background than they would if the background weren't there. Specifically, they behave as though they have mass. But before we explore that mechanism in detail, we need to understand how the universe arrived at this state. The Higgs field hasn't always had a non-zero value. In the earliest moments after the Big Bang, conditions were very different. Right after the Big Bang, the universe was extraordinarily hot. Temperatures were so extreme that the physics was fundamentally different from what we observe today. At these enormous temperatures, the Higgs field did not sit in the trough of its potential. It had enough thermal energy to sit at the top of the hump, at a field value of zero. The situation is like heating the wine bottle so much that the ball bouncing around has enough energy to stay near the top of the central hump rather than settling into the trough. At sufficiently high temperatures, the effective shape of the potential changes. The hump disappears and zero becomes the stable state. In this extremely hot early universe, with the Higgs field at zero, the fundamental particles behaved very differently from how they behave today. The W and Z bosons were massless. They behaved like photons. The weak nuclear force and the electromagnetic force were not separate forces. They were aspects of a single unified force called the electroweak force. The symmetry between them was unbroken, manifest, obvious. The W bosons, the Z boson, and the photon were all massless gauge bosons of this unified electroweak force. They were interchangeable in certain precise mathematical ways. The universe was symmetric. Think about what this universe would have looked like if you could somehow exist inside it. Every particle around you is moving at the speed of light. Nothing can slow down because nothing has inertia. The W bosons are zipping through space at light speed, just like photons. Electrons are massless and racing at the same universal speed. Quarks have no rest mass. There is no distinction between the electromagnetic force and the weak force. A W boson behaves just like a photon in many respects, mediating a force that reaches across unlimited distances. The universe at this moment is simpler, more symmetric, more uniform, but it is also structureless. There is nothing to build with, no atoms, no stable composite objects, no chemistry, just a blazing plasma of massless particles interacting through unified forces, hurtling through space at the speed of light, unable to stop, unable to clump, unable to form anything lasting. But the universe was cooling. As it expanded, the temperature dropped, and at some point, roughly 1/1,000,000,000th of a second after the Big Bang, the temperature dropped below a critical threshold, approximately 159 billion electron volts in energy equivalent. At this temperature, the shape of the Higgs potential shifted. The central hump became pronounced. The trough became the true lowest energy state, and the Higgs field, no longer having enough thermal energy to remain at zero, rolled off the hump and settled into the trough. It acquired its non-zero vacuum expectation value. This event is called electroweak symmetry breaking. It was one of the most important phase transitions in the history of the universe. Not a gradual shift, but a relatively sudden change in the character of physical law. Before this transition, the electroweak symmetry was intact. After it, the symmetry was broken. The Higgs field chose a non-zero value, and in doing so, it fundamentally changed the behavior of the W and Z bosons. They went from being massless to being massive. The electromagnetic force and the weak nuclear force, previously unified, became distinct. The photon remained massless, while the W and Z acquired enormous masses. The universe we know today, with its specific forces and particles, crystallized from this transition. The change was everywhere and instantaneous in a cosmic sense. It didn't start in one corner of the universe and spread. The field value shifted throughout all of space as the universe cooled through the critical temperature. One moment, the Higgs field was at 0, and all the electroweak gauge bosons were massless and interchangeable. The next moment, cosmically speaking, the field was at 246 billion electron volts, and the W and Z bosons had suddenly become among the heaviest particles in existence. The weak force, which an instant before had been long-range and powerful, collapsed to a range of roughly 1,000th the diameter of a proton. The photon, which an instant before had been indistinguishable from its electroweak siblings, was now alone as the sole massless carrier of the electromagnetic force. The rules of the game changed everywhere at once. Think of it like water freezing. Liquid water has a symmetry. It looks the same in all directions. There's no preferred orientation. But when water freezes into ice, the water molecules arrange themselves into a crystal lattice. The crystal has a preferred direction, the direction of the lattice planes. The symmetry is broken. The ice is less symmetric than the liquid water was. You can still see the ice. You can measure it. But the underlying symmetry that the liquid had is now hidden in the crystal structure. Something similar happened with the Higgs field. The underlying equations of the Standard Model have the electroweak symmetry built in. The mathematics is symmetric. But when the Higgs field settled into its non-zero value, the actual state of the universe became less symmetric than the underlying equations. The symmetry wasn't destroyed, it was hidden, spontaneously broken. The laws of physics still respect the symmetry at a deep level, but the specific configuration the universe ended up in does not make that symmetry obvious. This is what physicists mean by spontaneous symmetry breaking. The wine bottle analogy captures this nicely. The potential has a perfect circular symmetry. Every point on the trough is equivalent. There's no preferred direction, but the ball has to settle somewhere specific on the trough. Once it does, the symmetry is broken. The ball's position picks out a specific direction. The underlying potential is still symmetric, but the ball's actual state is not. Similarly, the Higgs field's potential has the full electroweak symmetry. But once the field settles into a specific non-zero value, the symmetry is broken. The specific value the field chose determines the masses of the W and Z bosons and distinguishes the electromagnetic force from the weak force. Before the symmetry broke, there was no distinction. After, the distinction is sharp and measurable. Now, let's be very precise about what the non-zero Higgs field is and what it isn't, because there are common misconceptions that can be misleading. The Higgs field background is not a substance filling space like air fills a room. It's not something particles push through and experience resistance from, the way a ball experiences resistance when pushed through thick syrup. This analogy is used sometimes in popular science, and while it captures a tiny sliver of the truth, it's mostly wrong. The Higgs field doesn't slow particles down. It doesn't create drag. Particles moving through the Higgs field background don't gradually lose speed the way objects moving through a fluid do. A particle moving through the Higgs field in empty space will continue moving at the same speed indefinitely. There is no friction, no drag, no viscosity. What the Higgs field does is change a particle's inertia. It changes how hard it is to accelerate the particle. It changes how the particle responds to forces. A particle interacting strongly with the Higgs field has a large mass, meaning it resists changes in its motion more. A particle interacting weakly with the Higgs field has a small mass, meaning it's easier to accelerate. A particle that doesn't interact with the Higgs field at all has zero mass and moves at the speed of light. This is the case for the photon. The distinction between drag and inertia is crucial. Drag is a force that opposes motion. If the Higgs field created drag, particles would slow down over time and eventually stop. That doesn't happen. Inertia is resistance to changes in motion. A massive particle is hard to start moving, hard to stop, hard to turn. But once it's moving at a constant velocity, it stays at that velocity unless a force acts on it. The Higgs field gives particles inertia, not drag. Mass is inertia, not friction. Another misconception is that the Higgs field is something added to space, something extra layered on top of an otherwise empty vacuum. This isn't right either. The Higgs field is part of what defines the vacuum. The vacuum isn't empty space plus the Higgs field. The vacuum is the state where all fields are in their ground states, including the Higgs field. And the Higgs field's ground state happens to be non-zero. The non-zero Higgs background isn't something placed in the vacuum. It is the vacuum, at least in part. It's part of the definition of what empty space is. This means the Higgs field's non-zero value is not some temporary condition that might change. It's not like a temperature that might fluctuate or an electric field that might turn off. The Higgs field is at its minimum energy at this non-zero value. To change it, to push it away from 246 billion electron volts, would require adding energy. Pushing the field to zero would actually increase the energy of the vacuum. It would be like pushing the ball back up to the top of the hump in the wine bottle. It would cost energy. The current non-zero value is the most stable, lowest energy state available. It is, as far as we know, permanent. There is a caveat to this permanence. Some theoretical calculations suggest the Higgs field might not be in the absolute lowest energy state. It might be in a metastable state, a local minimum rather than a global minimum. If that's the case, the field could, in principle, tunnel quantum mechanically to a lower energy state, a process that would be catastrophic for the universe as we know it. The constants of nature would change, particle masses would shift, atoms as we know them might not be stable. This is sometimes called vacuum decay, and it would propagate outward at the speed of light, destroying everything in its path. But before you lose sleep over this, know that even if the vacuum is metastable, its expected lifetime is inconceivably long. The calculations suggest it would last far longer than the current age of the universe, possibly longer than any meaningful timescale in physics. For all practical purposes, the Higgs field's current non-zero value is stable and permanent. Let's return to the moment of electroweak symmetry breaking and think about what it meant for the universe. Before this transition, roughly 1/1,000,000,000th of a second after the Big Bang, the universe was a hot, dense plasma of particles, all massless, all moving at or near the speed of light. The W and Z bosons were massless. The fundamental quarks and charged leptons were massless. Nothing had inertia in the way we understand it today. The particles zipped around at light speed, interacting with each other through the electroweak and strong forces, but without the property of mass. Then the Higgs field underwent its phase transition. The field value shifted from 0 to 246 billion electron volts, and instantly, the character of the universe changed. The W and Z bosons acquired enormous masses. They went from behaving like photons, traveling at the speed of light, to being sluggish, heavy particles that could only travel extremely short distances before decaying. The weak force, which had been long-range and unified with electromagnetism, became short-range and distinct. The quarks and charged leptons acquired their masses too, though much smaller than the W and Z masses. The universe went from a perfectly symmetric hot plasma to something more like the structured world we see today. This transition was not violent in the everyday sense. There was no explosion, no shockwave. The Higgs field simply settled into a new value, and the properties of all interacting particles changed accordingly. But the consequences were enormous. Without this transition, without the Higgs field acquiring its non-zero value, the universe could not have formed atoms. Without massive W and Z bosons, the weak force would have behaved differently. Without massive quarks, protons and neutrons would not have formed the way they did. Without massive electrons, atoms would not have formed at all. Everything about the structure of matter, everything about chemistry, everything about the physical world you interact with every day, traces back to this moment when the Higgs field settled into its non-zero value and broke the electroweak symmetry. Now, let's think about this from a slightly different angle. The Higgs field's non-zero value means that empty space is not truly empty in a very specific sense. Even in a perfect vacuum, even in a region with no particles of any kind, the Higgs field has a value. This background permeates everything. Every particle in the universe is immersed in it. There is no way to shield yourself from it, no way to create a region of space where the Higgs field is zero. It is, in a very real sense, part of the fabric of the universe as it exists today. This permanence is what makes the Higgs field so different from other sources of mass or energy. A gravitational field can vary from place to place. An electromagnetic field can be shielded. But the Higgs field background is uniform, constant, and inescapable. It doesn't come from any source in the traditional sense. There's no object generating it. It's not being broadcast or projected. It's simply the state that the Higgs field naturally occupies, everywhere, all the time, because that's where its energy is minimized. And this uniform background is what certain particles interact with to acquire mass. The interaction is happening right now, at every point in space, for every fundamental particle that couples to the Higgs field. It's not something that happened once in the early universe and then stopped. It's ongoing. The W boson has mass right now, because right now, at this very moment, the Higgs field has a non-zero value, and the W boson is interacting with that value. If you could somehow turn off the Higgs field, set it to zero everywhere, the W boson would instantly become massless. But you can't turn it off, because zero is not the lowest energy state. The field would immediately roll back to its non-zero value. This is fundamentally different from how mass works for composite particles like protons. A proton has mass for reasons that have mostly nothing to do with the Higgs mechanism, as we'll see. But for fundamental particles like the W boson, the Z boson, the electron, the quarks, and the other charged leptons, mass is a direct consequence of their continuous, unceasing interaction with the Higgs field background. The strength of that interaction varies from particle to particle. Different particles couple to the Higgs field with different strengths. The top quark, the heaviest known fundamental particle, couples very strongly. Its mass is about 173 billion electron volts, which means it interacts intensely with the Higgs background. The electron couples much more weakly. Its mass is only about 511,000 electron volts, roughly 340,000 times lighter than the top quark. The difference in mass reflects the difference in coupling strength. Particles that couple more strongly to the Higgs field are heavier. Particles that couple more weakly are lighter. These coupling strengths are parameters of the Standard Model. They're called Yukawa couplings, after the Japanese physicist Hideki Yukawa. They are not predicted by the theory, they are measured. The Standard Model tells you that if a particle has a certain Yukawa coupling, its mass will be that coupling multiplied by the vacuum expectation value of the Higgs field divided by the square root of 2. The formula is simple and elegant. But the theory does not explain why the Yukawa couplings have the values they do. Why is the top quark's coupling so large and the electrons so small? Why does the pattern of masses look the way it does? These are open questions. The Standard Model accommodates the masses but does not explain them at a deeper level. The photon does not couple to the Higgs field at all. Its Yukawa coupling is zero. That's why the photon is massless. It moves through the Higgs field background without interacting with it. The background might as well not be there as far as the photon is concerned. This is why light travels at the speed of light, and always has, even after electroweak symmetry breaking. The photon was massless before the transition, and massless after. The Higgs mechanism didn't affect it. The gluons, the carriers of the strong nuclear force, also remain massless after electroweak symmetry breaking. Like the photon, they do not acquire mass through the Higgs mechanism. But their story is different from the photons in other ways because of the nature of the strong force and the phenomenon of confinement. Gluons are never observed as free particles. They are always trapped inside composite objects like protons and neutrons. Neutrinos present a special case. In the original formulation of the Standard Model, neutrinos were massless. They did not couple to the Higgs field through Yukawa couplings. But experiments beginning in the late 1990s showed that neutrinos do have tiny masses, far smaller than any other massive fundamental particle. The discovery of neutrino oscillations, the phenomenon where one type of neutrino transforms into another type as it travels, proved that neutrinos have non-zero masses. How neutrinos get their mass is still an open question. It might involve the Higgs field through a different mechanism than the standard Yukawa coupling, or it might involve new physics beyond the standard model entirely. This is one of the major unsolved puzzles in particle physics. Now we arrive at the heart of the matter, the actual mechanism. How does a non-zero background field give particles mass? This is the question that drove some of the greatest minds in 20th century physics to develop one of the most elegant ideas in the history of science. And the answer, while mathematically precise, rests on a concept that is surprisingly intuitive once you see it clearly. Mass, for fundamental particles, is not an intrinsic property that particles simply have. It is a consequence of interaction. It is something that happens to particles because they cannot avoid coupling to a field that is always on. Let's build up to this carefully. Start with what mass actually means in physics. Most people think of mass as the amount of stuff in an object. That's a reasonable everyday definition, but it's not what physicists mean. In modern physics, mass is defined by two things. First, mass determines how a particle responds to forces. The more massive a particle is, the harder it is to accelerate. Push on something with a given force, and a massive particle accelerates slowly, while a less massive particle accelerates quickly. This is inertia. It's Newton's second law. Force equals mass times acceleration. Mass is the measure of how much a particle resists changes in its motion. Second, and this is deeply connected to the first, mass determines how a particle moves through space-time. In Einstein's special relativity, massless particles must travel at the speed of light. They have no choice. A photon is created, and it immediately moves at exactly 299,792.458 kilometers per second. It never speeds up, it never slows down. It is born at light speed, and it dies at light speed. There is no reference frame in which a photon is at rest. Massive particles, on the other hand, always travel slower than light. They can be at rest. They can be accelerated. They can move at different speeds depending on how much energy they have, but they can never reach the speed of light. The more energy you put into accelerating a massive particle, the closer it gets to light speed, but it never quite reaches it. Mass is what makes the difference between a particle that must travel at light speed and a particle that can sit still. So when we say the Higgs mechanism gives particles mass, what we mean is that it changes their fundamental behavior. Before interacting with the Higgs field, certain particles would behave like photons. They would be massless. They would travel at the speed of light. They would have no inertia. After interacting with the Higgs field's non-zero background, they behave differently. They travel slower than light. They can be brought to rest. They resist acceleration. They have inertia. The Higgs field doesn't add stuff to particles. It changes how they propagate through the universe. Let me explain the mechanism. In quantum field theory, how a particle moves through space is described by its propagator, a mathematical object that encodes everything about the particle's motion. For a massless particle, the propagator is simple. The particle moves at light speed, interacting with other fields, but never slowing down, never sitting still. For a massive particle, the propagator is different. It includes a mass term that modifies how the particle propagates. The mass term is what prevents the particle from reaching light speed and what gives it inertia. The Higgs mechanism generates this mass term through interaction with the background field. Here is how it works. Imagine a particle, say a W boson, moving through space. At every point in space, the Higgs field has its non-zero background value. The W boson couples to the Higgs field. This coupling is built into the mathematics of the electroweak theory. It's a consequence of the gauge symmetry structure. As the W boson moves, it is constantly interacting with the Higgs background. At every point, at every moment, it couples to the field value sitting there. This constant, unceasing interaction modifies the W boson's propagator. It adds a term to the equations governing the W boson's motion that is mathematically identical to a mass term. The W boson behaves exactly as though it has a mass, even though no mass was put in by hand. The mass arose dynamically from the interaction with the background. Let me try to give you a physical sense of why this works, because the mathematics alone doesn't convey the intuition. Think about what it means for a particle to interact with a background field at every point in space. A massless particle, left to its own devices, propagates freely at the speed of light. It moves in a straight line through space-time without interruption. Its motion is simple and unimpeded. But now fill all of space with a field that this particle couples to. The particle can no longer propagate freely. At every point along its path, it is interacting with the background. Each interaction is a tiny event, a coupling between the particle and the field value at that location. These couplings are not occasional. They are continuous, happening at every point, at every moment without exception. The cumulative effect of this constant interaction is that the particle's motion changes character. Instead of gliding through space at light speed as it would if the background weren't there, the particle is effectively being interrupted at every point. Not slowed down in the sense of friction, but altered in a more fundamental way. The continuous coupling to the background changes the relationship between the particle's energy and its momentum. For a massless particle, energy equals momentum times the speed of light. The particle moves at light speed always. But when the continuous interaction with the Higgs background is included, the relationship shifts. Energy no longer equals momentum times light speed. There is an extra term, a gap between the energy the particle has and the momentum it carries. That gap is the mass. The particle now needs a minimum amount of energy just to exist, even when it's sitting still. That minimum energy is its rest mass. This is why mass is inertia rather than drag. The Higgs background doesn't push against the particle's motion. It doesn't oppose movement. What it does is change the fundamental equation that relates the particle's energy to its momentum. It introduces a rest energy, a minimum energy cost for the particle's existence. And a particle with rest energy has inertia. It resists acceleration, because accelerating it requires adding energy on top of the energy it already has, just from existing. The more rest energy, the more inertia, the more mass. The strength of this effect depends on two things. It depends on how strongly the particle couples to the Higgs field, and it depends on the value of the Higgs field background. The mass of a particle equals its coupling strength to the Higgs field, multiplied by the vacuum expectation value of the field, with a factor involving the square root of 2, depending on the specific type of particle. Since the vacuum expectation value is the same for everyone, approximately 246 billion electron volts, the different masses of different particles arise purely from their different coupling strengths. This is an extraordinary feature of the Higgs mechanism. There is one field with one background value, and it gives rise to all the different masses of all the fundamental particles that couple to it. The electron's tiny mass, the top quark's enormous mass, the intermediate masses of the muon and tau and the other quarks, all of them come from the same field. The only thing that differs is how strongly each particle talks to that field. Now, let's focus on where the Higgs mechanism matters most and where it was originally motivated. The W and Z bosons. These are the particles that carry the weak nuclear force, and their story is the reason the Higgs mechanism was proposed in the first place. The weak nuclear force is responsible for certain types of radioactive decay. When a neutron decays into a proton, an electron, and an antineutrino, that process is mediated by the weak force. A down quark inside the neutron emits a W- boson, transforming into an up quark. The W- boson then decays into the electron and antineutrino. Without the weak force, this decay could not happen. Without the weak force, the sun could not shine, because the nuclear fusion reactions at the sun's core depend on the weak force to convert protons into neutrons. The weak force is carried by three bosons, the W+, the W-, and the Z. The W+ and W- carry electric charge. The Z is electrically neutral. All three are massive. The W bosons have a mass of about 80.4 billion electron volts. The Z boson has a mass of about 91.2 billion electron volts. These are enormous masses. They are roughly 85 to 97 times the mass of a proton. These particles are heavy, and this heaviness has a direct physical consequence. It determines the range of the weak force. Forces carried by massless particles, like electromagnetism carried by the photon, have infinite range. The electromagnetic force between two charged particles falls off with distance but never reaches zero. It extends across the entire universe. That's because the photon is massless and can travel any distance without decaying. But forces carried by massive particles have limited range. The more massive the carrier, the shorter the range. This is because massive particles require energy to create, and quantum mechanics allows them to be borrowed from the vacuum only for very short times and very short distances. The range of the force is inversely proportional to the mass of its carrier. For the W and Z bosons, with their enormous masses, the range works out to about 10 to the negative 18 meters. That's roughly 1/1000th the diameter of a proton. The weak force operates only at incredibly tiny distances. Two particles must be almost on top of each other for the weak force to act between them. This is why the weak force seems weak. It's not that the underlying coupling is particularly small. The weak force's coupling constant is actually comparable to the electromagnetic coupling constant. The force appears weak because it has such short range. In most situations, particles aren't close enough for the weak force to matter. But when particles are extremely close together, as they are inside atomic nuclei, the weak force becomes important. It drives certain nuclear reactions, certain types of radioactive decay, and certain processes that are essential for the existence of matter as we know it. All of this depends on the W and Z bosons being massive. If they were massless, the weak force would be long range, just like electromagnetism. It would reach across large distances. The universe would look completely different. Nuclear physics would be completely different. Atoms would be completely different. Stars would be completely different. The Higgs mechanism, by giving mass to the W and Z bosons, is directly responsible for the weak force having the short range it does. It shapes the character of one of the four fundamental forces of nature. But here's the problem that the Higgs mechanism solved, and understanding the solution requires appreciating just how severe the problem was. The electroweak theory, which unified the electromagnetic and weak forces, was built on gauge symmetry, and as we saw, gauge symmetry strictly forbids mass terms for force-carrying particles. The photon being massless was fine, but the W and Z bosons are among the heaviest fundamental particles known. The theory needed them massless for mathematical consistency, but nature made them massive. The contradiction seemed fatal. The physicists working on this problem in the early 1960s knew the theory was too good to abandon. The electroweak unification explained too many experimental results, predicted too many relationships between measurable quantities to be wrong. The mathematics was beautiful and powerful. It just couldn't accommodate massive force carriers without breaking. So the question became not whether gauge symmetry was right, but whether there was a way to keep the symmetry in the equations while allowing the particles to behave as though they were massive. The answer turned out to be yes, but it required a completely new idea. The solution was breathtaking in its cleverness. You don't give the W and Z bosons mass directly. You don't write a mass term in the equations. Instead, you introduce the Higgs field with its special potential, the Mexican hat potential, and you let the field settle into its non-zero ground state. The underlying equations of the theory retain the full gauge symmetry. The symmetry is not violated at the level of the laws of physics, but the actual state of the universe, with the Higgs field sitting at a non-zero value, does not respect the symmetry. The symmetry is spontaneously broken. When you work out the mathematics of this spontaneous symmetry breaking, something remarkable happens. The Higgs field has four components. This is a technical detail that matters enormously. The Higgs field is not a single number at every point in space. It is a set of four numbers. These four components are required by the mathematical structure of the electroweak theory. They transform together under the electroweak symmetry in a specific way. When the field settles into its non-zero value, three of those four components are absorbed by the W+, the W-, and the Z boson. This absorption is one of the most extraordinary processes in all of theoretical physics. Each of these three gauge bosons eats one component of the Higgs field, and in doing so, acquires mass. The language physicists use, eats, sounds whimsical, but it describes a precise mathematical process. The Higgs component doesn't disappear. It becomes part of the gauge boson. It provides the gauge boson with something it didn't have before, a new degree of freedom, a new way to vibrate. Here is what that means physically. Before the symmetry breaking, the W and Z bosons had only two polarization states each, the two transverse polarizations that massless particles possess. A polarization state describes the direction in which a wave vibrates relative to its direction of motion. A massless particle like a photon can vibrate left or right, or up and down, perpendicular to its direction of travel. These are its two transverse polarizations, but it cannot vibrate along its direction of motion. A massless particle has no longitudinal polarization. This isn't just a rule, it's a mathematical consequence of traveling at the speed of light. At light speed, there is no rest frame, and without a rest frame, longitudinal polarization is not a meaningful concept. After eating a Higgs component, each W and Z boson gained a third polarization state, a longitudinal one. They could now vibrate along their direction of motion. This is something only massive particles can do. Massive particles have rest frames. They can sit still, and when they move, they can oscillate in the direction they're traveling. The extra degree of freedom, the longitudinal polarization, came directly from the absorbed Higgs field component. The Higgs component didn't vanish. It became the longitudinal mode of the gauge boson. It became part of the particle's physical identity. This is sometimes described by saying the W and Z bosons gained their mass by swallowing part of the Higgs field. 3 of the 4 Higgs components became the longitudinal polarizations of the 3 massive weak bosons. The 4th component, the remaining one, is the physical Higgs boson, the particle that was discovered at the Large Hadron Collider in 2012. So the Higgs boson is, in a sense, the leftover, the surviving piece of the Higgs field after 3 components were consumed to give mass to the W and Z bosons. This is why the Higgs boson has spin 0. It's the remaining scalar component. The 3 eaten components became part of spin 1 vector bosons. The 4th component stayed as a spin 0 scalar particle. This is elegant in a way that's hard to overstate. The same field that solves the mass problem also explains the count of degrees of freedom. Before symmetry breaking, you have 4 massless gauge bosons with 2 polarizations each, that's 8 degrees of freedom, plus 4 Higgs field components, making 12 total. After symmetry breaking, you have 1 massless photon with 2 polarizations, 3 massive gauge bosons with 3 polarizations each, that's 9, and 1 physical Higgs boson. 2 plus 9 plus 1 equals 12. Everything is accounted for. No degrees of freedom are created or destroyed, they're just rearranged. The mathematics is perfectly consistent. The photon, crucially, does not eat a Higgs component. It does not acquire mass. The specific pattern of symmetry breaking ensures that one combination of the original gauge fields remains massless. That combination is the photon. The other combinations become the massive W and Z bosons. This is why electromagnetism survives as a long-range force after electroweak symmetry breaking, while the weak force becomes short-range. The photon remains massless, while the W and Z become heavy. One force reaches across the universe, the other barely reaches across a proton. The masses of the W and Z bosons are determined by 2 things: the vacuum expectation value of the Higgs field, which is 246 billion electron volts, and the gauge coupling constants of the electroweak theory. You can write simple formulas. The W boson mass equals the vacuum expectation value multiplied by the weak coupling constant divided by 2. The Z boson mass equals the vacuum expectation value multiplied by the square root of the sum of the squares of the weak coupling constant and the hypercharge coupling constant, again divided by 2. These formulas were written down before the W and Z bosons were experimentally discovered, and when those particles were found at CERN in 1983, their measured masses matched the predictions beautifully. This was one of the great triumphs of the Standard Model. Now let's turn to the quarks and the charged leptons, the particles that make up ordinary matter. These particles also acquire mass through the Higgs mechanism, but through a slightly different mathematical structure. The quarks and charged leptons don't eat components of the Higgs field the way the W and Z bosons do. Instead, they acquire mass through what are called Yukawa interactions. A Yukawa interaction is a direct coupling between a fermion, like a quark or electron, and the Higgs field. The strength of this coupling is a number called the Yukawa coupling constant. Each fermion has its own Yukawa coupling constant, and the values of these constants determine the fermion masses. The formula is straightforward. The mass of a fermion equals its Yukawa coupling constant multiplied by the vacuum expectation value of the Higgs field divided by the square root of 2. Since the vacuum expectation value is fixed at 246 billion electron volts, the mass of each fermion is directly proportional to its Yukawa coupling constant. The top quark has a Yukawa coupling of about 0.99, very close to 1. This gives it a mass of about 173 billion electron volts, making it the heaviest known fundamental particle. It is so heavy that it is roughly as massive as an atom of gold. A single fundamental particle with the mass of an entire atom. The top quark's Yukawa coupling is uniquely large. No other fermion comes close. The bottom quark has a Yukawa coupling of about 0.024, giving it a mass of about 4.2 billion electron volts. The charm quark's coupling gives it a mass of about 1.27 billion electron volts. The strange quark sits around 93 million electron volts. The down quark is approximately 4.7 million electron volts. The up quark is the lightest quark at about 2.2 million electron volts. Among the charged leptons, the tau has a mass of about 1.78 billion electron volts, corresponding to a Yukawa coupling of about 0.01. The muon has a mass of about 105.7 million electron volts, and the electron, the lightest charged lepton, has a mass of about 511,000 electron volts. Its Yukawa coupling is approximately 0.000003, incredibly tiny. The electron barely interacts with the Higgs field compared to the top quark, and this is reflected in its comparatively minuscule mass. This pattern of Yukawa couplings, spanning roughly 6 orders of magnitude from the top quark to the electron, is one of the great unsolved puzzles of particle physics. The standard model does not predict these values, it accommodates them. You can plug them in, and the theory works perfectly. But the theory doesn't tell you why the top quark's coupling is 1,000,000 times larger than the electrons. It doesn't explain why there are 3 generations of quarks and leptons, rather than 2 or 4 or 17. The Yukawa couplings are free parameters, numbers that must be determined by experiment rather than derived from principle. This is important because it marks a boundary of our understanding. The Higgs mechanism explains how fundamental particles get mass, but it does not explain why they have the specific masses they do. The mechanism provides the framework, the machinery, but the detailed numbers, the coupling strengths that determine each particle's mass, are inputs to the theory rather than outputs. Understanding where these numbers come from might require physics beyond the standard model, deeper principles that we haven't yet discovered. Let's also address 2 particles that conspicuously do not acquire mass through the Higgs mechanism, the photon and the gluons. The photon, as we discussed, remains massless after electroweak symmetry breaking. The pattern of symmetry breaking is such that one specific combination of gauge fields remains untouched. This combination is the photon. It does not couple to the Higgs field in a way that would give it mass. It passes through the Higgs background completely unaffected, continuing to travel at the speed of light, continuing to mediate the electromagnetic force over infinite distances. The gluons, the 8 carriers of the strong nuclear force, are also massless. This is because the strong force's gauge symmetry, described by the mathematical group called SU3, is not broken by the Higgs field. The Higgs mechanism specifically breaks the electroweak symmetry, the SU2 times U1 symmetry. It does not touch the strong force symmetry. So gluons remain exactly massless, just as the mathematics of an unbroken gauge symmetry requires. However, gluons behave very differently from photons, despite both being massless. Gluons carry color charge, the charge of the strong force. Because they carry color charge, they interact with each other, unlike photons, which don't interact directly with other photons. This self-interaction leads to confinement. Gluons can never be isolated. They are always trapped inside composite particles like protons and neutrons. You will never detect a free gluon traveling across space the way you detect photons. So while gluons are massless in the equations, their practical behavior is nothing like the photons. They are massless but confined, a strange combination that has no analogue in everyday experience. Now, let's zoom out and appreciate what the Higgs mechanism accomplishes as a whole. Before electroweak symmetry breaking, you have a symmetric theory with massless gauge bosons and massless fermions. After the Higgs field settles into its non-zero value, the W and Z bosons acquire mass by absorbing components of the Higgs field. The quarks and charged leptons acquire mass through their Yukawa couplings to the non-zero Higgs background. The photon and gluons remain massless. The symmetry is hidden, but the theory stays mathematically consistent. Calculations remain finite and meaningful. Probabilities stay between 0 and 1. Everything works. This consistency is not a minor technical detail. It is the entire reason the Higgs mechanism was proposed. Without it, the electroweak theory would have been mathematically sick. Predictions would have produced infinite or nonsensical results. The theory would have been useless for calculations at high energies. The Higgs mechanism doesn't just explain mass, it saves the mathematical integrity of the standard model. It's the piece that makes the whole framework coherent. And it was tested, not just by finding the Higgs boson, but by a long sequence of precision measurements over decades. The electroweak theory, with the Higgs mechanism included, made precise predictions about the properties of the W and Z bosons, their masses, their decay rates, how they interact with other particles, how they are produced in collisions. These predictions were tested at particle colliders like the Large Electron-Positron Collider at CERN and the Tevatron at Fermilab. Every measurement matched the predictions. The agreement between theory and experiment was extraordinary, sometimes matching to better than 1 part in 1,000. In fact, the precision of these measurements was so good that physicists could use them to predict the approximate mass of the Higgs boson before it was discovered. The Higgs boson appears in loop corrections, subtle quantum effects where virtual Higgs bosons briefly appear and disappear in the course of other processes. These virtual contributions affect measurable quantities in tiny but calculable ways. By comparing precise measurements with precise theoretical calculations, physicists could determine that the Higgs boson mass had to be in a certain range. When the Higgs was finally discovered at about 125 billion electron volts, it fell squarely within that predicted range. The entire framework was consistent. Everything fit. This is the power of the Higgs mechanism. It's not just a qualitative story about a field giving mass to particles. It's a quantitative, precise, testable mathematical framework that has been confirmed by decades of experiments to extraordinary accuracy. The masses of the W and Z bosons, the detailed behavior of the weak force, the properties of the Higgs boson itself, all of it follows from the Higgs field settling into its non-zero value and the mathematical consequences that follow. But there is a crucial caveat that we've been building toward, a misconception so widespread that it has become nearly universal in popular science. The claim that the Higgs field gives mass to everything. You've heard it said that the Higgs boson is responsible for all mass, that without the Higgs field, nothing would have mass, that the Higgs is the origin of mass in the universe. This is misleading. The Higgs field gives mass to fundamental particles. The W and Z bosons, the quarks, the electron, the muon, the tau, these are the particles whose masses arise from the Higgs mechanism, and for these particles, the mechanism is genuinely responsible for their mass. An electron without the Higgs field would be massless. A top quark without the Higgs field would be massless. The W boson without the Higgs field would be massless. This is all true. But most of the mass of ordinary matter, the mass of the stuff you're made of, the mass of atoms, the mass of your body, does not come primarily from the Higgs mechanism. Most of the mass you carry around every day has a completely different origin, and understanding that origin is essential to getting the full picture of what mass really is and where it really comes from. Here is the fact that changes everything. You are made of atoms. Atoms are made of electrons orbiting a nucleus. The The nucleus is made of protons and neutrons, and the mass of an atom comes almost entirely from its nucleus. The electrons contribute very little. In a hydrogen atom, the single electron accounts for less than 1/20th of 1% of the atom's total mass. The rest is the proton. In heavier atoms, the proportion is even more extreme. The electrons are negligible. The mass of ordinary matter is overwhelmingly the mass of protons and neutrons. So if you want to understand where your mass comes from, you need to understand where the proton's mass comes from. And this is where the popular story about the Higgs field goes wrong, because the proton's mass does not come primarily from the Higgs mechanism, not even close. A proton is made of quarks, specifically 2 up quarks and 1 down quark, bound together by the strong nuclear force, which is carried by gluons. The up quark has a mass of about 2.2 million electron volts. The down quark has a mass of about 4.7 million electron volts. Add those up. 2 up quarks plus 1 down quark gives you a total quark mass of roughly 9.1 million electron volts. But the proton's mass is about 938.3 million electron volts. The quarks account for only about 9.1 million electron volts out of 938.3 million. That's less than 1%. Roughly 99% of the proton's mass has nothing to do with the masses of the quarks inside it. And since the quark masses are the part that comes from the Higgs mechanism, this means roughly 99% of the proton's mass has nothing to do with the Higgs field. Let that sink in. When people say the Higgs field gives everything its mass, they're leaving out the fact that for ordinary matter, the kind of matter that makes up you and me and the Earth and the Sun, about 99% of the mass comes from somewhere else entirely. So where does the rest come from? The answer lies in Einstein's most famous equation, E equals mc squared. This equation tells you that energy and mass are equivalent. They are two forms of the same thing. Energy has mass. Mass is energy. If you have a system with a lot of energy, that system has mass, even if the individual components are light or even massless. Inside a proton, the quarks are not sitting still. They are flying around at enormous speeds, close to the speed of light, confined to the tiny volume of the proton by the strong nuclear force. The gluons that carry the strong force between the quarks are also present in huge numbers, constantly being emitted and absorbed, constantly creating virtual quark-antiquark pairs that pop into existence and immediately annihilate. The interior of a proton is an extraordinarily violent, dynamic, energetic environment. It is seething with activity at all times. All of this activity represents energy, the kinetic energy of the quarks as they zip around at near light speed. The energy stored in the gluon fields that bind them together. The energy of the virtual particles constantly being created and destroyed. This energy is enormous compared to the rest masses of the quarks themselves. And because energy and mass are equivalent, all of this energy contributes to the proton's mass. This is not the Higgs mechanism. This is quantum chromodynamics, or QCD, the theory of the strong nuclear force. QCD describes how quarks and gluons interact. It's one of the most successful and well-tested theories in all of physics. And one of its most important consequences is that the binding energy inside a proton, the energy of the strong force holding the quarks together, accounts for the vast majority of the proton's mass. Let me be more precise about this. In QCD, the strong force has a remarkable property. It gets stronger as you try to pull quarks apart. If two quarks are close together, the force between them is relatively weak. They can move somewhat freely. But if you try to separate them, the force increases. It's like a rubber band. A little stretch and the force is gentle. A big stretch and the force becomes enormous. At sufficiently large distances, the force is so strong that you can never isolate a single quark. Before you can pull a quark free, the energy you've invested in stretching the gluon field becomes large enough to create a new quark-antiquark pair from the vacuum. The new quark binds to the one you were trying to free, and you end up with two composite particles instead of one isolated quark. This property is called confinement. Quarks are permanently confined inside composite particles called hadrons. of which protons and neutrons are the most familiar examples. You can never see a free quark. No matter how hard you try, no matter how much energy you use, the strong force will always create new quarks before letting one escape. Confinement is why the strong force dominates the interior of protons and neutrons, even though its individual carrier particles, the gluons, are massless. The energy associated with this confinement, the energy stored in the gluon fields, the kinetic energy of the quarks rattling around inside their tiny prison, the energy of virtual particles constantly flickering in and out of existence, all of this energy adds up to about 929 million electron volts for a proton. That's the difference between the proton's total mass and the combined rest masses of its 3 quarks. Almost the entire mass of the proton is this binding and kinetic energy, not the Higgs-generated quark masses. And this is not just a theoretical claim. It has been verified computationally to remarkable precision. Physicists have developed a technique called lattice QCD, where the equations of quantum chromodynamics are solved numerically on supercomputers. The idea is to approximate spacetime as a discrete grid, a lattice of points, and then simulate the behavior of quarks and gluons on that grid. You start with nothing but the fundamental equations of QCD and the small quark masses as inputs. Then you let the computer calculate what happens when quarks and gluons interact according to those equations. And what comes out is the proton mass. The computer calculates the mass of a proton from first principles, and the result matches the experimentally measured value to within a few %. This is one of the most impressive achievements in computational physics. It confirms that the proton's mass really does come overwhelmingly from the energy of the strong force, not from the Higgs-generated masses of the quarks inside it. The calculation has been refined over decades as computers have become more powerful and algorithms more sophisticated, and every improvement has brought the result closer to the measured value. The physics is clear. The proton's mass is QCD energy made manifest through E equals mc squared. This is one of the most remarkable facts in physics. The mass of the objects around you, the mass of your body, the weight you feel when you stand on a scale, roughly 95% of it comes from the energy of the strong force inside protons and neutrons. It comes from E equals mc squared applied to the roiling, chaotic energy inside every atomic nucleus. It does not come from the Higgs field acting on quarks. If you could somehow turn off the Higgs field, setting it to 0 everywhere, the quarks would become massless. The electron would become massless. The W and Z bosons would become massless. But protons and neutrons would still have most of their mass. The binding energy of QCD would still be there. The strong force would still confine quarks. The gluon fields would still carry enormous energy. Protons would be slightly lighter, by about that 1% contribution from the quark masses, but they would still exist and still be massive. The vast majority of the mass of ordinary matter survives even without the Higgs field. Of course, a universe without the Higgs field would be utterly different from ours in other ways. Massless electrons would travel at the speed of light and could never be captured into orbits around nuclei. Atoms as we know them could not form. Chemistry would not exist. Life would not exist. The Higgs field is absolutely essential for the universe we inhabit, but not because it generates most of the mass. It's essential because it gives mass to the right particles in the right way to allow atoms, molecules, and complex structures to exist. The electron's tiny mass, generated by its interaction with the Higgs field, is what allows electrons to be bound into atoms. Without that mass, electrons would be massless, and the electromagnetic force could not trap them. So the precise statement is this: the Higgs mechanism is responsible for the masses of fundamental particles. It gives mass to the W and Z bosons, the quarks, and the charged leptons. These masses are crucial for the structure of the universe, but most of the mass of ordinary composite matter, the mass of protons, neutrons, atoms, and everything built from them, comes from the binding energy of the strong force described by quantum chromodynamics. The Higgs provides the small quark masses. QCD provides the large proton mass. Both are essential. Neither alone tells the complete story. Now let's turn to the discovery itself and what it actually confirmed. The Higgs boson was found at the Large Hadron Collider on the 4th of July, 2012, by two independent experiments called ATLAS and CMS, at a mass of approximately 125 billion electron volts. That discovery was the culmination of a nearly 50-year search. But the discovery was only the beginning. What mattered next was not just that the particle existed, but whether it behaved exactly as the standard model predicted. And this is where the real work began. Producing a Higgs boson is extraordinarily rare. Out of the billions of proton collisions that occur at the Large Hadron Collider every day, only a tiny fraction generate the right conditions. And when a Higgs boson is created, it vanishes almost immediately, in about 1.6 times 10 to the negative 22 seconds, decaying into other particles. Physicists never see the Higgs boson directly. They see its decay products and reconstruct what must have existed a moment before. This is forensic physics. You study the debris and work backward to identify the source. The Higgs boson can decay in several different ways. It can decay into two photons. It can decay into two Z bosons, which themselves decay into four charged leptons. It can decay into two W bosons. It can decay into a bottom quark and a bottom antiquark. It can decay into two tau leptons. Each of these decay channels has a predicted rate, a branching ratio that the standard model calculates precisely. If the Higgs boson were different from what the standard model predicts, if it had different couplings or a different internal structure, these branching ratios would be different. Measuring them is the most direct way to test whether the discovered particle really is the standard model Higgs boson or something else. In the years since the discovery, physicists have measured the Higgs boson's properties in detail. Its spin has been confirmed as zero, its parity has been measured. Its couplings to other particles, how strongly it interacts with W bosons, Z bosons, bottom quarks, tau leptons, and other particles, have been measured and compared to standard model predictions. In every case, the measurements are consistent with the standard model. The Higgs boson behaves exactly as the theory predicted. This is both triumphant and slightly frustrating. Triumphant because it confirms the Higgs mechanism, one of the most important ideas in modern physics. The theoretical framework proposed in 1964 has been verified by experiment to remarkable precision. The standard model, with the Higgs mechanism included, is an extraordinarily successful theory. It describes the behavior of fundamental particles and forces with a level of accuracy that is almost unprecedented in the history of science. But it's slightly frustrating because physicists were hoping for surprises. The standard model, for all its success, has known shortcomings. It doesn't include gravity. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't explain why the universe contains more matter than antimatter. It doesn't explain why the Yukawa couplings have the values they do. It doesn't explain why there are 3 generations of quarks and leptons. There are many things the standard model doesn't address. Physicists hoped that studying the Higgs boson would reveal cracks in the standard model, hints of new physics beyond it. So far, the Higgs boson has been disappointingly well behaved, matching every standard model prediction without deviation. But there is one profound mystery associated with the Higgs boson that remains unsolved, and it is one of the deepest puzzles in all of theoretical physics. It's called the hierarchy problem. The Higgs boson has a measured mass of about 125 billion electron volts. In the context of particle physics, this is a moderate mass. It's heavier than most fundamental particles, but much lighter than the energy scales where gravity becomes important, the Planck scale, which is about 10 to the 19th billion electron volts. The ratio between the Higgs mass and the Planck scale is about 1 to 10 to the 17th. That's an enormous gap, roughly 100 million billion. The hierarchy problem asks why this gap exists and why it's stable. In quantum field theory, the Higgs boson's mass receives quantum corrections. Virtual particles constantly pop in and out of existence, interacting with the Higgs boson and affecting its mass. These corrections tend to push the Higgs mass up toward the highest energy scale in the theory. If you include gravity, that highest scale is the Planck scale. The quantum corrections want to make the Higgs boson enormously heavy, roughly 10 to the 19th billion electron volts, not the relatively light 125 billion electron volts we observe. For the Higgs mass to come out at 125 billion electron volts, the underlying parameters of the theory must be fine-tuned to extraordinary precision. The large quantum corrections must nearly cancel, leaving only a tiny residual that gives the observed mass. The degree of cancellation required is roughly 1 part in 10 to the 34. It's like adding and subtracting enormous numbers and having them cancel to leave a tiny remainder. Each number might be 30 digits long, but their difference is only a few digits. This seems incredibly unlikely, unless there's some deeper reason for the cancellation. Several theoretical frameworks have been proposed to solve the hierarchy problem. Supersymmetry, one of the most studied extensions of the Standard Model, proposes that every known particle has a partner particle with different spin. The quantum corrections from the known particles and their supersymmetric partners would naturally cancel, stabilizing the Higgs mass without fine-tuning. But no supersymmetric particles have been found at the Large Hadron Collider, despite extensive searches. If supersymmetry exists, the partner particles must be heavier than current experiments can reach, which introduces its own degree of fine-tuning. Composite Higgs models propose that the Higgs boson is not a fundamental particle, but a bound state of new particles held together by a new force, similar to how pions are bound states of quarks. In these models, the Higgs mass is naturally set by the binding energy of the new force, and the hierarchy problem is softened. But no evidence for the new particles or new force has been found. Extra-dimension models propose that gravity is actually as strong as the other forces, but appears weak because it dilutes itself across additional spatial dimensions. In some versions, the Higgs mass is naturally stabilized by the geometry of the extra dimensions. But again, no evidence for extra dimensions has appeared in experiments. The hierarchy problem remains open. It's possible that one of these proposed solutions is correct, and we simply haven't reached the energy scales needed to see the evidence. It's possible that a completely different solution exists that no one has thought of yet. And it's possible, though unsatisfying to many physicists, that the fine-tuning is just a brute fact of nature, with no deeper explanation. Perhaps the universe simply has the parameters it has, and there's no reason beyond the anthropic observation that different parameters wouldn't allow observers to exist. There are other open questions surrounding the Higgs field and boson. One of the most fundamental is why the Higgs potential has the shape it does. Why does the Higgs field have a non-zero vacuum expectation value? The Mexican hat potential, with its central hump and surrounding trough, is put into the Standard Model by hand. The theory doesn't derive it from deeper principles. The parameters that determine the shape of the potential, the quadratic and quartic couplings, are measured from experiment. But why do they have the values they have? Why is the quadratic term negative, which is what creates the hump at zero and makes the non-zero value energetically preferred? A deeper theory might explain this, but we don't have one yet. Another open question is whether the Higgs boson is truly fundamental, or whether it has structure at scales we haven't yet probed. Current experiments show no deviation from the predictions of a fundamental scalar particle, but our measurements have finite precision. There could be structure at smaller scales that we simply can't resolve yet. Future colliders operating at higher energies might reveal such structure, or they might confirm that the Higgs boson really is fundamental, down to the smallest accessible scales. There's also the question of whether there is only one Higgs boson, or whether there are more. The Standard Model requires exactly one Higgs doublet, which after symmetry breaking produces one physical Higgs boson. But many extensions of the Standard Model predict additional Higgs bosons. Supersymmetric models typically require at least 2 Higgs doublets, producing 5 physical Higgs particles, 2 of which would be charged. Other models predict different numbers. Searching for additional Higgs bosons is a major goal of current and future collider experiments. Finding a second Higgs boson would be unmistakable evidence for physics beyond the Standard Model. The Higgs field also connects to cosmology in deep and not fully understood ways. The vacuum expectation value of the Higgs field contributes to the energy of empty space, the cosmological constant that drives the accelerating expansion of the universe. But when you calculate the expected contribution from the Higgs field, you get a number roughly 56 orders of magnitude larger than the observed cosmological constant. This monstrous disagreement, sometimes called the worst prediction in the history of physics, suggests something profound is missing from our understanding. Either there are enormous cancellations from unknown sources, or our understanding of vacuum energy is fundamentally incomplete. The Higgs field might also have played a role in cosmic inflation, the brief period of exponential expansion in the very early universe that explains why the observable universe is so uniform and flat. Some models propose that the Higgs field itself, or a close relative, could be the inflaton, the field that drove inflation. The Higgs boson's measured mass and the Higgs potential's measured shape are marginally compatible with certain inflation models, though the connection remains speculative and is being tested through observations of the cosmic microwave background. There is even a connection to the stability of the universe itself. As we know, the Higgs field might sit in a metastable state rather than the absolute lowest energy state. What makes this particularly striking is that the measured mass of the Higgs boson and the measured mass of the top quark place the standard model tantalizingly close to the boundary between absolute stability and metastability. These two numbers, the Higgs mass at 125 billion electron volts and the top quark mass at 173 billion electron volts, together determine the shape of the Higgs potential at extremely high field values. And the shape they imply sits right at the edge. Slightly different values would push the universe clearly into one category or the other. We won't know for certain which side we're on until we measure both masses more precisely, which is one of the goals of future collider experiments. Let's step back now and consider what the Higgs field tells us about the nature of reality. There is something philosophically striking about the fact that one invisible field, present everywhere, never turning off, existing since a trillionth of a second after the Big Bang, is responsible for whether fundamental particles have mass or not. Without this field's non-zero value, the universe would be a completely different place. Particles would fly around at the speed of light, no atoms would form, no stars would ignite, no planets would coalesce, no life would emerge. The universe would be a hot, formless, structureless soup of massless particles and radiation, expanding and cooling but never building anything complex. The Higgs field made structure possible. It made atoms possible. It made chemistry possible. It made you possible. Not because it provides most of the mass in the universe, it doesn't, but because it provides the right masses to the right particles in the right amounts to allow the incredible complexity we observe. The electron's mass, tiny as it is essential. It determines the size of atoms, the energy of chemical bonds, the behavior of materials. If the electron's mass was significantly different, chemistry would change. Atoms might not form the stable structures they do. The specific value of the electron's mass, set by its Yukawa coupling to the Higgs field, is part of what makes the periodic table possible. The masses of the quarks, though they contribute only a small fraction to the proton's total mass, are also important. They determine the mass difference between the proton and neutron, which in turn determines the stability of hydrogen and the balance of nuclear reactions in stars. Small changes in quark masses would change which nuclei are stable, which would change the elements that exist, which would change the chemistry that's possible, which would change whether life as we know it could arise. And the W and Z boson masses determine the character of the weak nuclear force, which governs certain types of radioactive decay and is essential for the nuclear reactions that power stars and produce the heavy elements that planets and living things are made of. Without massive W and Z bosons, the weak force would be long-range, and the physics of nuclear reactions would be completely different. Everything connects. The Higgs field's vacuum expectation value, the coupling constants, the resulting masses, the character of the forces, the structure of matter. Pull on any one thread, and the whole tapestry unravels. The universe we inhabit is exquisitely sensitive to the properties of the Higgs field, and we don't fully understand why those properties are what they are. This is where physics stands today. We have discovered the Higgs boson. We have confirmed the existence of the Higgs field. We have measured its properties and found them consistent with the standard model. We understand the mechanism by which the Higgs field gives mass to fundamental particles. We understand that this mechanism is not the whole story of mass, that the majority of the mass of ordinary matter comes from the strong force binding energy inside protons and neutrons. We understand the mathematical framework with extraordinary precision, but we don't understand why. We don't know why the Higgs potential has the shape it does. We don't know why the vacuum expectation value is 246 billion electron volts and not some other number. We don't know why the Yukawa couplings span such a vast range. We don't know whether there are additional Higgs bosons. We don't know whether the Higgs boson is truly fundamental or secretly composite. We don't know how the Higgs field connects to gravity, to dark matter, to dark energy, to the matter-antimatter asymmetry. Each of these questions is a doorway. Behind each one might be an entirely new layer of physics, as revolutionary as quantum mechanics was to classical physics, as transformative as Einstein's relativity was to Newton's mechanics. The Higgs boson might be the key that opens those doors, or it might be a perfectly well-behaved particle that tells us exactly what the standard model predicted, and nothing more. We won't know until we look more carefully, at higher energies, with greater precision, over longer timescales. What we do know is remarkable enough. There exists a quantum field, the Higgs field, that fills all of space with a non-zero background value. This field has existed since roughly 1/1,000,000,000th of a second after the Big Bang. It defines part of what we mean by empty space. Every fundamental particle in the universe is immersed in it, and has been since the moment the field settled into its current state. Certain particles interact with this field, and through that interaction, they acquire mass. They gain inertia. They become sluggish, resistant to acceleration, unable to reach the speed of light. Other particles ignore the field entirely and remain massless, forever travelling at light speed. The Higgs boson is the quantum excitation of this field. It is the ripple that appears when energy is concentrated in the field. It is fundamental as far as we know. It has no known internal structure. It has spin zero, unique among all known fundamental particles. It was predicted in 1964 and discovered in 2012, nearly half a century later, at the most powerful particle accelerator ever built. Its discovery confirmed the Higgs mechanism and completed the standard model of particle physics. But the Higgs boson is not the Higgs field. The boson is temporary, the field is permanent. The boson is rare, requiring enormous energy to produce and lasting for an incomprehensibly brief instant. The field is ubiquitous, filling every point in space at every moment without exception. The boson was discovered at a specific time and place by specific detectors. The field has been here all along, since the earliest moments of the universe, quietly and universally shaping the properties of every fundamental particle that exists. The next time someone tells you that the Higgs boson gives everything its mass, you'll know the fuller story. The Higgs field, not the boson, is the key player. And even the field doesn't give everything its mass. It gives mass to fundamental particles. Most of the mass you carry around, the mass of the protons and neutrons inside your atoms, comes from the fierce energy of the strong force, from quarks and gluons in violent quantum motion, from the equivalence of energy and mass that Einstein revealed over a century ago. Mass has more than one origin. The Higgs field provides one piece. Quantum chromodynamics provides another. Together, they account for the mass of the visible universe. And together, they represent two of the deepest insights in all of physics. One field that breaks a symmetry and gives fundamental particles their inertia. One force that binds quarks so tightly that its energy becomes the mass of nearly everything you've ever touched. The universe is built from fields. Those fields fill all of space. Some of them sit at zero when undisturbed. One of them does not. And because that one field refuses to rest at zero, because its lowest energy state is something rather than nothing, particles have mass, atoms exist, stars shine, planets form, and you are here to wonder about all of it. The Higgs field is not just a mechanism in particle physics. It is one of the conditions that made a structured, complex, knowable universe possible. And understanding it, even partially, even imperfectly, is one of the most extraordinary achievements of the human mind. But the central message remains clear. The Higgs field is unlike any other field we know. It has a non-zero value in empty space, a value that arose when the universe cooled below a critical temperature shortly after the Big Bang. This non-zero background is permanent, uniform, and inescapable. It fills the entire universe. It defines part of what we mean by empty space. And it is this background, not the Higgs boson itself, that is responsible for giving mass to certain fundamental particles. The boson is the excitation. The background is the mechanism. The universe you live in, the universe of massive particles, of atoms, of chemistry, of stars and planets and life, exists because the Higgs field's lowest energy state is not zero. If nature had been even slightly different, if the shape of the Higgs potential had placed the minimum at zero instead of at 246 billion electron volts, none of this would exist. The W and Z bosons would be massless. The weak force would be long range. The electromagnetic and weak forces would be unified and indistinguishable. Electrons would have no mass. They would travel at the speed of light and could never be bound into atoms. There would be no atoms, no molecules, no chemistry, no biology, no stars as we know them, no planets, no you. The entire visible universe, everything with structure, everything with complexity, everything we observe and experience, depends on the Higgs field having settled into the right non-zero value at the right moment in cosmic history. It is one of the most consequential events that ever occurred. Not because something dramatic exploded or collided, but because a field, quietly and everywhere at once, shifted from zero to a value that made matter possible. And this brings us to the deepest question. How exactly does this non-zero field value translate into mass? What is the physical mechanism? How does interacting with a background field make a particle resist acceleration? This is the Higgs mechanism, and it is one of the most beautiful ideas in all of physics.